Hello everyone and welcome back to our channel where we help you to learn science by making it fun and easy. Today we're going to take a look at Newton's second law of motion, one of the most important laws in all of physics. We'll explain what it means, why it's so important, and give you some real-world examples. So let's get started. Newton's second law of motion is one of the cornerstone principles of classical mechanics formulated by Sir Isaac Newton in the late 17th century. It describes the relationship between the motion of an object and the forces acting upon it. In simpler terms, Newton's second law of motion states that the acceleration of an object is directly proportional to the net external force acting on it and inversely proportional to its mass. Mathematically, this is represented as F equals ma, where F is the force, m is the mass, and a is the acceleration. To better understand this concept, let's break down each part of the equation. First, the force acting on an object can cause it to accelerate or change its velocity. This change in velocity over time is known as acceleration. If no force is applied to an object, it will remain at rest or continue moving with a constant velocity. However, when a force is applied, the object will start to accelerate in the direction of the force. The greater the force, the greater the acceleration. This is the first part of Newton's second law of motion, the direct proportionality between force and acceleration. The second part of the equation is the mass of the object. Mass is a measure of the amount of matter in an object and is also a measure of the object's inertia. Inertia is the tendency of an object to resist changes in its state of motion. An object at rest tends to stay at rest, and an object in motion tends to stay in motion with the same speed and in the same direction unless acted upon by a force. The more massive an object is, the greater its inertia, and the less it will accelerate under a given force. This is the inverse proportionality between mass and acceleration. Now that we have a basic understanding of the individual components of the equation, let's put them together to see how they work as a whole. Newton's second law of motion tells us that the product of the mass and acceleration of an object is equal to the force acting on the object. Rearranging the equation, we can solve for acceleration. A equals F per meter. This equation shows us that acceleration is directly proportional to force and inversely proportional to mass. Now let us look at a few examples to see how Newton's second law of motion works in the real world. One common example is a car accelerating on the road. When a car starts from rest and accelerates to a certain speed, it is subject to a number of forces, including the force of the engine, the force of friction, and the force of gravity. The force of the engine is what propels the car forward, and the force of friction is what opposes the motion of the car. The force of gravity acts downward, but it does not affect the acceleration of the car because it is balanced by the normal force from the road. Since the forces of gravity and normal force cancel each other out, the net force acting on the car is equal to the force of the engine minus the force of friction. According to Newton's second law of motion, the acceleration of the car is directly proportional to the net force acting on it. Therefore, as the force of the engine increases, the acceleration of the car also increases. As the force of friction increases, the acceleration of the car decreases. Another example is a rocket taking off into space. A rocket is subject to the force of gravity, which acts downward, and the force of the engines, which acts upward. Initially, the force of gravity is greater than the force of the engines, so the rocket accelerates upward. As the rocket gains height, the force of gravity decreases because the mass of the rocket decreases as it expels gases. At the same time, the force of the engines remains constant. As the force of gravity decreases and the force of the engines remains constant, the net force acting on the rocket increases, causing the rocket to accelerate faster. Eventually, the rocket reaches a point where the force of the engines is equal to the force of gravity. At this point, the net force acting on the rocket becomes zero, and the rocket stops accelerating and moves at a constant velocity. This is known as free fall. One more example to add to our list is a ball thrown upward. When a ball is thrown upward, it is subject to the force of gravity, which acts downward. The force of gravity causes the ball to decelerate as it rises. The ball reaches its highest point when its velocity becomes zero. After this point, the ball accelerates downward due to the force of gravity until it hits the ground. The acceleration of the ball is directly proportional to the force of gravity and inversely proportional to the mass of the ball. This is why a heavier ball falls faster than a lighter ball. Let's now look at some implications of Newton's second law of motion. The first implication is that the acceleration of an object is directly proportional to the net force acting on it. This means that if the net force acting on an object increases, the acceleration of the object will also increase. Conversely, if the net force acting on an object decreases, the acceleration of the object will also decrease. For example, if you push a shopping cart with a force of 10 newtons, it will accelerate in the direction of the force. If you then increase the force to 20 newtons, the acceleration will double. The second implication is that the acceleration of an object is inversely proportional to its mass. This means that if the mass of an object increases, the acceleration of the object will decrease. Conversely, if the mass of an object decreases, the acceleration of the object will increase. For example, If you push a 10 kilograms box across the floor with a force of 10 newtons, it will accelerate in the direction of the force. If you then push a 20 kilograms box with the same force, the acceleration will be half as much. The third implication is that the units of force, mass, and acceleration are related to each other in a specific way. According to Newton's second law of motion, force is equal to mass times acceleration. This means that the units of force are equal to the units of mass times the units of acceleration. In the International System of Units, the unit of force is the newton, the unit of mass is the kilogram, and the unit of acceleration is meters per second squared. Therefore, 1 newton is equal to 1 kilogram meter per second squared. In conclusion, Newton's second law of motion is a fundamental principle of physics that explains the relationship between the motion of an object and the forces acting on it. The law states that the acceleration of an object is directly proportional to the net external force acting on it and inversely proportional to its mass. This law has numerous applications in engineering and physics and is essential for understanding the behavior of objects in motion. From rockets to cars to balls thrown into the air, Newton's second law of motion helps us to predict how objects will move under the influence of various forces. By understanding this law, we can design machines and structures that can withstand the forces acting on them and ensure that they move in the desired manner. So whether you're launching a rocket into space or simply throwing a ball to a friend, remember to take into account Newton's second law of motion. We hope you enjoyed learning about Newton's second law of motion. If you did, please like and share this video with your friends. And don't forget to subscribe for more fun science videos. Thanks for watching, and we'll see you next time. If you want to keep learning, here are some videos that we think you'll enjoy. They're also from our channel, and they cover some really interesting topics. So click on the video that you want to watch, and let the learning begin.